I'd like to invite PacSci EMC to the podium, and we'll get started.
Great, thank you, Tom. My name's Steve Nelson. I'm with Pacific Scientific Energetic Materials Company. I'm here with my colleagues Peter Current and Brett Umsberg. Peter's our rocket motor expert and Brett's our electronics expert, so they'll be here to help answer questions. And I'd also like to thank NASA and the NIA for this opportunity. We were very honored to be selected as a finalist. Very unexpected, but we're happy. Okay, so what do we do? Who are we? We create solutions to protect human life. If a rogue nation launches a ballistic missile at us or our allies, we have systems that help to destroy the missile. If a fighter pilot ejects, we have systems to help control the event. If a launch vehicle goes off course, we have systems to terminate its flight. So we have a tagline, we make critical missions possible. We have some technology that helps make that happen. And what we want to do is use this capability in the new space market. We are an established company. We're a little different than the startups that are here, but we think we have a unique technology to move into new space. So we'll talk about why we're here. Why is new space so interesting? It's the red line and the green line. It's 20% compounded annual growth, and that's very interesting to us, right? We always look for high growth markets. So that's a very simple explanation. Okay, what problem are we trying to solve? Majority of cube, micro, and small sats today have no onboard propulsion. They have no drag makeup capability, orbit adjust, collision avoidance, or deorbit capability. And why not? Right now, the existing propulsion systems are kind of scaled down versions of large satellite technology. But they tend to have power consumption problems, especially for small sats. They fly with pressurized tanks and liquid propellant sometimes, and that can cause launch problems. We have a company we're working with that flew a propulsion system empty because they wouldn't let them launch it with propane, simple propane propulsion system. And they tend to have fittings, tubing, valves, and the valves tend to be non-hermetic, and so cold and warm gas can leak out. And in the case of electric propulsion, they have extremely low thrust. And I'm not knocking these things. I mean, electric propulsion is great for going on from here to Mars. You're going to have to use it because the efficiency is so high. But in low Earth orbit, there are some issues, including magnetic torquing in some cases. Okay, so what's the solution? We call it MAPS, or Modular Architecture Propulsion System. And what we've done is we basically take the energy that's in a liquid propellant tank, we kind of quantize it into a bunch of small solid rocket motors. And we can extend the orbital life of small sats by years, so constellation operators don't have to replenish the constellations often, save a lot of money there. We don't have tanks, valves, fittings, or heaters. It's a plug-and-play bolt-on design. And instant on. We can be on in 5 milliseconds. We completely power off, power us on. 5 milliseconds later, you can be producing thrust. So for responsive space, it's got some application there. Very low power, always. We're less than 5 watts, even when you're firing motors. It's got variable thrust. You can fire pairs of motors. You can fire quads. You can fire triples. You can fire them all if you want to break your satellite, but probably don't want to do that. And it's adaptable and scalable. We fit in volumes that typically aren't used. So in the right-hand side of the slide, you see our light band propulsion system. It fits inside the light band, which is typically unused space on a space vehicle or satellite. We have 176 motors in there, and that'll provide about 55 meters per second for a 100 kilogram satellite. So you could use it to deorbit or make some minor orbit adjustments or do all the things we talked about. The lower right-hand side, you can see it's only about 4 inches tall. Upper left-hand side is a much bigger version. That was for a customer that wanted to do a lot more delta V. That's 350 meters per second on a 100 kilograms spacecraft. And then in the middle, at the bottom, that's actually an upper stage system, about 15 inches in diameter. And that's for a small launch vehicle company. That'll raise its orbit from 200 kilometers up to about 400 kilometers. So we have a lot of potential application in this market. And we actually have the IP on this. Our patent was allowed about a month ago. And we're filing a continuation patent to add some electronics to it. I have a video coming up kind of showing you conceptually how it works. There we are on orbit. We fire a motor to rotate the satellite, fire another motor to stop the rotation, do a delta V maneuver, boost the orbit a little bit. Again, very shallow system. We can also command other things on the satellite if we want to use our control electronics. And satellites at end of life, we rotate into the anti-ram direction. Fire a motor to stop it, and then we do our dramatic deorbit. Our animators made this go for about 2 minutes. They loved the fire, so I cut it off for you. Didn't want to bore you. Peter, is there anything else you want to say about the motors? Peter's our rocket motor expert, so I thought I'd have him comment.
Yeah, so the rocket motors, we're EMC, right? So that's my kind of focus, is the old school, the material science of it in terms of the propulsion. And so as you saw in the video, there's a couple key points to that. One is when the timing of the rockets is off a little bit, it causes a rotation. So for us, the ignition system is extremely important. So we're coupled with the electronics, and Brett will talk a little bit about the electronics, but we use a reactive silicone semiconductor bridge to initiate the propellant in it. And it gives us, microsecond timing. So the difference in the video, you see a number of motors fire up. You can use the small quants in series with literally no break in propulsion and keep the thrust levels low, but keep a nice continuous burn. Additionally, the propellant itself, we have two types of propellant selected. One that we're firing in our current spacecraft, which he'll talk about a little bit later in terms of the spacecraft, but it's a standard HTDB. It does great for fairly high radiation environments. It's relatively clean burning. There is some condensants that come out of it. So because of that, it gives us a nice an ISP, in the over 250. But for more sensitive applications where you have optics on board that don't have covers, things of that nature, we actually have a propellant that is 100% clean burning. It's an all gas effluent plume with no condensate whatsoever.
Thanks, Peter. Okay, so what about workflow? Liquid propulsion system. I'm picking on these because I used to do these at TRW Space and Defense. So I'm very familiar with them. So they typically involve lots of welds and fittings and valves and filters and tanks, and all that has to be put together, and it's typically put together by a skilled technician, very skilled at welding, and everything has to be very clean. Liquid propellants don't like contamination. So there's quite a bit of time, touch labor to assemble that. Then it has to be put into the propulsion module or the satellite, however you're going to do it. A lot of mechanical assembly, pressure testing, leak testing. Then you ship the satellite and or the propulsion system to where you're going to launch. And if you're using hydrazine, you ship the hydrazine separately, the hazmat material, ground only. And if you're using kind of less toxic, ammonia-based green liquid propellants, you can ship those fine, no problem. So it's not an issue for shipping. But then once you get to the launch site, you have to fuel your satellite or your propulsion system. And that's pretty extensive operation. There's a lot of ground support equipment that goes with it. It takes quite a bit of time. Somewhat hazardous operation because you're dealing with pressurized gases and liquid propellants. So there's quite a bit of workflow involved in using a liquid system on a satellite. So our projection is we could save about 5 months in customer workflow, either on the front end where the satellite manufacturer, the propulsion system manufacturer is making the propulsion system, or where the satellite manufacturer is integrating it into their satellite. So our Our cartridge-based rocket motor approach lends itself really well to automation. We build, in some cases, thousands and thousands of cartridge devices per year on automated machines. So if we get into significant volumes, we can actually implement this. You can automate grain machining, motor assembly and weld, helium leak check. We want to make sure every cartridge is hermetic. And PCB assembly and soldering. The backplane of this system is an electronic board, so that lends itself really well to automated manufacturing. We can ship to the launch site on their standard carrier, and we have ways to do that with these systems. And then one of the big benefits is once you get there, you bolt it on. I mean, literally bolt it on and plug it in. So, there's no fueling there. The fuel's already in the motors. So the 2 days might be a little long. I'm thinking probably 5 hours or 4 hours, half a day type thing. So that's probably a little generous. So we believe we can save significant time. A skilled technician over 5 months, working with an engineer assembling these things, that can be $250,000, $500,000 of savings per satellite. The other thing I should mention before I do that is because our propulsion system's kept completely separate from the customer satellite, if something goes wrong with the propulsion system, let's say the liquid system, and they have to fix it, the whole system has to be sent back to wherever to be repaired. Because we're completely independent and we can ship the propulsion system to the launch site, the cost of rework is much improved. And our heritage kind of comes out of the tactical world. We built an RPG killer, an active protection system with a prime. We made the round though. You'll see our round popping up, pitching over with our rocket motors. We fire a booster motor and a small warhead to kill the RPG. You'll see a side view here coming up. So this is our round coming up. We fire a pitch over motor to rotate it. Fire another one to stop it so it's inertially in the right space. We fire a booster motor to go get the RPG. And again, the warhead. In the next scene, you'll see real time. Boom, got it. So that's the exact same technology we're proposing to use. For new space. We would have slower burning motors though. That all happened in 100 milliseconds. So for space, clearly they probably don't want that kind of thrust level and impulse delivery time. But in addition to that, we've been on missile defense systems with this technology, hypersonic missiles, countermeasure systems, guided mortars and munitions, space radiation tests, and on-orbit exposure. We actually use this technology downhole to frack wells as well. So we've it's pretty versatile. And then we built our own satellite. We built PacSci Sat. We launched it June 22nd on PSLV 38. And we're generating data. We fired up the system, 4 initiators, everything worked great. So we're calling ourselves Technology Readiness Level 9. We're going to fire the rocket motors at the end of this month, so we haven't done those yet. Okay. Another benefit of having a distributed array of rocket motors is you tend to induce limited angular momentum into the spacecraft. Because we're randomly installed, any impulse mismatch between motors, if you fire them in pairs, kind of cancels out over time. If you have a fixed liquid or solid nozzle, the CG offset tends to be there all the time. So you build up a lot of angular momentum over the mission. So we have a little benefit there. Now we have hundreds of rocket motors. How do you talk to them? How do you fire all these things? Well, we have an electronics system called SmartEnergetics Architecture. It's a control electronic system for firing off ordnance devices. And we stole it from the automotive industry. Actually, we didn't steal it. We paid a lot of money for it. It was developed for the automotive industry 10 years ago, actually early 2000s. Safe by wire, it's called. It's a specification, industry standard spec. The trouble was it's too expensive for the automotive world, so they didn't want it, so we went in and bought the IP from Philips. and we've adapted and improved the architecture for use in aerospace and defense. And then quite simply, here's our handout for money. Let's try to show the size. Trying to show the size of the controller card. That card will fire 48 devices. It talks over a network bus to the smart rocket motors. Each rocket motor has an address in it with an ASIC. It's a analog and digital bus. Both conditions have to be perfect or it won't work. We also have 3 independent inhibits for safety, so it's a very safe system. You can't get it to fire unless you really want it to, but it's also very reliable. It fires when it should. Again, we fire in 300 microsecond increments. And this is our team. We've got we're about a 40-year-old company, so we've got an experienced team from top to bottom. Our electronics manufacturing facility exists. We can really do this stuff. So what we're looking for, we have a $1 million funding gap for the non-recurring engineering. We've invested $1 million in the Philips semiconductor. RUAG OneWeb dispenser sequencer, we're going to dispense the OneWeb satellites, so we won that contract, but we invested $500,000, and PacSci Sats $1.5 million. Total investment's $3 million, and so we're looking for a co-investment of about $1 million. Questions?
So from your cartridge, I take it that each one of your propellants is in a cartridge, fires one time, and then you lose that. So you start losing your lever the more you fire for your control. How do you compensate for that, or you just say that that's the life of the control system? Yeah, so you have algorithms to know where you fired and where you haven't. And as long as the total impulse is available, you can rotate the spacecraft with the attitude control system if you need to. You can always get pairs into the right position if you need to. So there's not an issue operationally with firing in pairs or triples or whatever. If you're doing attitude control stuff, then you do have to do a little bit more positioning of the satellite. So the disc itself can move to put the cartridge in the right position? But if the satellite can rotate, right, with an attitude determination control system. Okay.
So typically it's used in conjunction with reaction wheels. So you can rotate the satellite to whatever position you want to fire, and then generally speaking, over a longer mission period, then you can use the attitude control system to spin down the reaction wheels to have a momentum transfer and bring the reaction wheel speeds down.
You might have said, but I don't remember it. What is the? Do you have different sizes? You called it modular. I'm assuming the modularity is in the cartridges, but in the package itself, do you have different sizes for different types of satellites?
Yeah, so we do. It's modular in 2 different ways. One, we do different sizing of the cartridges depending on what we call them quants.
Yep.
The energy quants that were required. So we can customize it in that way. And then also the real key is in the packaging in terms of fitting it into the spaces that's available currently, so that we're not intruding in useful space for the mission. Yeah. So it allows us to place it in very strange areas to optimize how much impulse they get. And sometimes they have us stick it on different ends because they'll just go ahead and flip the satellite over and fire in that way and flip back.
And do you have any comparisons of the mass or your system compared to traditional liquid propulsion?
That's a good question. So if you're building a lot of little tiny motors, our mass fraction tends to suffer. But for delta V type operations, we're very comparable with liquid systems. 50% and higher, better.
What's your IP? Did
So
you
we,
go over that if I missed it?
yeah, so we have our patent was accepted, what do they call it, about a month ago for the system, the actual system. We have a lot of IP on the underlying electronics, on the SmartEnergetics Architecture system, and we just got an allowance for the actual MAPS concept.
What is the stability, long-term stability and temperature constraints on the system?
For the electronics, it's very wide range. We're talking minus 50 to about 125 C. So for stability, and you can turn it on and off, so it doesn't need, like as Steve mentioned, on in about 5 milliseconds. So you can actually leave the system off without any power drain for the duration of the life, and then say you need to deorbit after 10 years or so, you can turn it on 5 milliseconds. You've used very little power, and you'll have, every time.
Yeah, so for propellants, the electronics are kind of the driver, really. The propellants, especially the composite, has no problem in those temperature ranges whatsoever. It has an extremely long life in those temperature range. The clean propellant's a little bit more sensitive to high temperatures in terms of it starts to self-degrade to a point. So, and that's at the higher temperatures. Generally speaking, because we're mounted in a large aluminum plate directly to the spacecraft's bus, and generally we're looking at LEO type of orbits for the CubeSat and SmallSat type of arrangements, the temperature profile is pretty mild because of the speed around. So it's constantly switching from light side to dark side. So we've seen that the temperature range has been relatively tight for those type of operations where they require clean propellant.
You showed a couple of examples that had maybe 2 burns. I assume you're coupled in rotation and translation and all that, so they're probably, is it a right assumption that you do rotational and do several burns depending on you want to
Right, so
those?
we take the customer's mission requirements, their minimum burns required, right? Getting back to the size of the rocket motors, if they have to do a lot of little tiny maneuvers, we build little small cartridges, right? And so we kind of take the customer's mission and optimize the solution for them.
Did you provide the dimensions of your the complete pallet or whatever that is? Is that geared to like a 1U?
Yeah, so we actually at our tabletops, we actually have hardware you can look at. But yeah, we do half U, 1U. The 1U do about 100 meters per second on a 3 or 4 kilogram CubeSat. The half U does about 55. So again, and to Peter's point, a lot of people are designing where they put motors in different places and move the satellite around to fire.
Right. So I'm wondering if you have categories of these, like for a 1U or a 3U or 6U space platform, and also if we could you'd be amenable to work to have customized physical dimensions and locations, so it doesn't have to be like that in case you have a really unique science craft.
Pretty much every customer wants off the shelf, and then once you talk to them, it's completely customized.
Is it going to be cost affordable? Or is it really going to blow the budget of how much it costs to make these little
relative to liquid systems? We're very affordable. I don't want to say an order of magnitude less, but maybe factor 3 or 4. So all that labor that goes into welding up the system and fueling the system, we tend to be a lot more cost effective.